Okay, Hassan, so continuing on with our examination of organic compounds, we've looked at a number of these here. So press pause at this point and try and take a look at these, fill in these blanks. So if you look at things, what we've done so far, we know that carbon compounds, which contain only carbon and only hydrogen, those are our hydrocarbons. They can be further subdivided to our aliphatics and our aromatics. If they don't contain a benzene ring, it's an aliphatic. If they do contain a benzene ring, it's an aromatic. Within the aliphatics, there are the alkanes, and the alkynes, and they can form ring compounds, which you attach the prefix cyclo in front of them. But before we continue further, we have to understand, and you should remember this from your Chem 20, that there are a number of different intermolecular forces that have an influence on the strength of the bonds within the molecule, which determines in natural process what the boiling points and melting points of these compounds would be. These include our Lund dispersion forces, our dipole-dipole interactions, and hydrogen bonding. All those were elaborated with you in your Chem 20. So what I want to do today is I want to get into some of the derivatives, the halides and the alcohols. So take a look, folks. Let's take a look at this here, son.
So an organic halide, that's a hydrocarbon in which the hydrogen atoms has been substituted with a halogen atom. So properties of organic halides, they have higher boiling points than similar hydrocarbons. Among the organic halides, iodines have the highest boiling points, followed by the bromides, chlorides, and fluorides in that order. And many are toxic or carcinogenic, so not good things to be around. Generally, organic halides are insoluble in water, but they're more soluble than similar hydrocarbons. The organic halides, they're good solvents for things like waxes, gums, fats, oils, resins, and rubbers. So examples of some organic halides are things like chloromethane. Here we see a hydrogen has been substituted for a chlorine atom. 1,2-difluoroethane. Here we have a double bond and we have two fluoride atoms at present, so difluoro. And 1,4-dibromobenzene. Two bromine atoms attached to a benzene ring. So how do we name organic halides? If we're taking a look at this compound that's shown right here, we see that we have some fluoride atoms present. So how do we identify it and name it? Well, the first thing that we need to do is we need to identify the root by looking at the parent chain. And that parent chain, that's that longest continuous chain of carbon atoms. So in this case right here, I see I have 1, 2, 3, 4, 5, 6, 7 carbon atoms in the parent chain. Then I have to look at my chart, which I've memorized, and know that my root must be hept. So I'll write that down. The next thing that I'll have to do is identify what the suffix is. In this case, we're still dealing with a hydrocarbon single bonded chain, so our suffix is -ane, and we have to identify where those organic halides are. So, and for that, we need to use our prefixes. The prefixes, they're going to identify the location and type of any side groups or branches in the molecule that are attached to that root or parent chain. So in this molecule right here, the side chains that I have are my halides. I have 2 fluorines here attached to that main chain. Now halogens, they are labeled with things like bromo for bromine, fluoro for fluorine, chloro for chlorine, and iodo for iodine. So those are our prefixes, and if there's more than one of those side groups and they're the same, then we're going to use di for 2, tri for 3, and tetra for 4, etc. These prefixes, we're not counting them when we're determining the alphabetical order of the prefixes. So what we're going to do is take a look at this. We see we have 2 fluorine atoms here, so we're going to call this difluoroheptane. However, we need to indicate where those fluorine atoms are on the parent chain. So to do that, we need to number the parent chain so that the side groups have the lowest number possible. So what I'm going to end up doing is I'm going to start numbering on this side of the molecule. If I start numbering over here, I see that this fluorine atom is attached to carbon 3, and this fluorine atom is attached to carbon number 4. Had I started numbering over here, this would be on number 4 and number 5, not as good. So we'll stick with numbering over here so we have the lowest prefixes possible. So in this case, this molecule would be named 3,4-difluoroheptane.
So that's the organic halides. Now, again, remember, the role these play is actually in determining the strength of bond. So just to double check this, it's on. The role that these bonds play, these intermolecular forces play, is that they relate to the strength of the attraction between molecules, subsequently impacting the boiling points and melting points of compounds. Covalent bonds are very strong by comparison. Intermolecular forces, by comparison, are relatively weak. To that end, we can compare and contrast them. The role of ion dipole forces, hydrogen bonding, dipole-dipoles, ion-induced dipoles, dipole-induced dipoles, and dispersion forces, Lund dispersion. They all play a role in the attractive force between molecules, which subsequently plays a role in the chemical properties and physical properties of compounds as well. But jumping to the organic halides. In short, an organic halide is a compound, an organic compound, where one or more hydrogen is replaced with a halogen. Chlorofluorocarbons, they contain chlorine and fluorine. Now, how you name them? Similar change, except now we change name. A chlorine, it's a chloro. Fluorine, fluoro. Bromo, ido, etc. General formula, R attached to an X, where X is the halogen atom. That's the functional group which influences the properties. So what do we need to know? Now, firstly, these may or may not be polar or nonpolar molecules. Electronegativity plays a role in determining that. They will have higher boiling points than similar hydrocarbons because they will have a low solubility in water, but they'll have a higher solubility than similar hydrocarbons. Typically, they're good solvents for various organic materials such as fats and oils and waxes, gums and resin and rubbers, but they do tend to be toxic. They do tend to be ecologically damaging. So to name them, again, this is covered off in your textbook on page 418. That's been posted. Now, let's take a look. 2,2,5-tribromo 5-methylhexane. We know that first off, that this molecule is based on a hexane molecule. 6 carbons. Let's draw those. We know that we have side chains. At carbon 2, and carbon 2, and carbon 5, we have bromo. So bromines attached to it. We also have at carbon number 5, a methyl group. 1 carbon side chain. Of course, the rest are all hydrogens. There, fluorine, fluoro, chlorine, chloro, Br, bromo, and iodo. Now, let's take a look at this one. This organic halide. Same as before, we start with the longest continuous chain, 1, 2, 3, 4, 5, 6, 7. All single bonds, therefore it's an alkane, therefore its root is heptane. Our side chains, we numbered alphabetically when there's choice. So we number this would be carbon 1, 2, 3, 4, 5, 6, 7. So this would be 2 bromo, 5 or 4 rather, chloro, heptane. How about this one? Now, for me, look at this here. Sometimes you see this alternating structure. It could be a bit, but let's name this one as if it was a cycloalkene. We number the carbons according to 1 to give the lowest numbers possible, 3, 4, 5, 6. There are 3 double bonds. So this would be 1, 3, 5, cyclo triene, 2 chlorine groups attached to carbons 1 and 2. So this would be 1, 2, dibromo 1,3,5 cyclotriene. 1,2 dichloroethane, 2 carbon, carbon to carbon. At carbon number 1, a chlorine. Carbon number 2, a chlorine. 1,2 dichloroethane. 2,2,5 tribromo 5-methylhexane. Again, a 6 carbon group, the hexane. At carbon 2 and 2 and 5, we have bromines. We also have a methyl group at carbon number 5. CH3, Cl2. CH3, Cl2. Or CH2Cl2, sorry. So carbon with 2 H's and 2 chlorines. This would be dibromomethane. Benzene ring. Chlorobenzene. 2 carbons. Ethene. Okay. Two bromines attached to carbon 1 and 2. 1, 2, dibromoethene. Now 1, 2 dibromo, 1, 2 dichloroethane. Carbon, carbon, 2. 1, 2 dichloro. 1, 2 dibromo. But it's an alkane, all single bonds. So we always know there's lots we can do. Now, the other thing too is that when you look at a bond, such if the side chains appear on the same side of the double bond, that's cis. Opposite sides, such as we see here, that's trans. Okay. So for organic halides, they may be polar, nonpolar, higher boiling points because of their molecular structure, low solubility, typically good solvents. They can be made through addition reactions by adding the constituent to the alkenes, to the alkynes. Or maybe you have a substitution reaction where something is already saturated, such as an aromatic, such as an alkane. You've got the and hydrogen must come off. This brings us now to the next group, the alcohols. The alcohols contain an OH functional group or a hydroxyl group. General formula are the rest of the molecule attached to this hydroxyl. Now, they'll be primary, secondary, or tertiary, depending on how many carbons are bonded to carbon that contains the alcohol. For example, this one here, it's a terminal. This is a primary alcohol. It's at the end. There's only 1 carbon attached to it, this carbon. It's secondary if you have a carbon on either side, such as here. So this is butan 1-ol, butan 2-ol, methylpropane 2-ol, 3 carbons. Therefore, a tertiary alcohol versus secondary versus primary. So let's take a look once again, folks.
In this video, you will learn some of the chemical properties of alcohols, how to classify alcohols, and some uses of the alcohols. Alcohols are organic molecules with the hydroxyl functional group, which is an oxygen bonded to a hydrogen, OH. Here is methane. Replace a hydrogen with the alcohol functional group to form methanol. Here is ethane. And here is ethanol, propane, and propanol. Pause the video and name this molecule. This was butanol. Did you get it right? The general formula of the alcohols is CnH2n plus 1 OH. The OH group generally makes alcohols polar molecules. The hydroxyl group also gives rise to hydrogen bonding. In our video on fractional distillation, we discussed how increasing chain length increased the boiling point due to increased intermolecular forces. The alcohols follow this same trend, but their boiling point is even higher than their comparable alkanes, and this is due to the hydrogen bonding. Alcohols are placed in one of 3 categories: primary, secondary, or tertiary, based on the position of the OH on the chain. Alcohols will react differently depending on the category they are in. In a primary alcohol, the carbon atom on which the OH group is bonded is itself attached to only one carbon chain or one alkyl group. Here is propan 1-ol. The OH is attached to the end carbon, and this carbon is attached to just one single chain of carbons. In secondary alcohols, the carbon atom on which the OH group is bonded is attached to 2 carbon chains or 2 alkyl groups. Here is propan 2-ol. Here is the carbon atom on which the OH is attached, and here you can see the 2 alkyl groups or 2 chains of carbons attached to this carbon. In tertiary alcohols, there are 3 carbon chains attached to the carbon on which the OH group is attached. As you can see, the carbon attached to the OH group is attached to 3 alkyl groups, making it a tertiary alcohol. It is important to categorize an alcohol as they have slightly different chemical properties. A good example of this that you could look into as further reading would be the oxidation of alcohols, with different reactions occurring for primary, secondary, and tertiary alcohols. Different alcohols have different uses at home and in industry. Ethanol is of course a common alcohol used in beverages, but it is also an important antiseptic. Ethanol can be made by 2 main methods: by fermentation and by the hydration of ethene. We have made a video on these molecules to learn about these methods in more detail. Other uses of alcohols are as fuels, preservatives, and solvents. Now, at the end of this tutorial, you should be able to identify the alcohol functional group, name alcohols, understand their uses, and be able to categorize them as primary, secondary, or tertiary.
So that's the alcohols, Hassan. So as you continue this there, remember, in naming alcohols, very similar before, long continuous chain that contains the hydroxyl. This is the key thing. It has to contain the hydroxyl group. Name the parent alkane, maybe an alkyne, maybe an alkene, but you start with that. You take the E at the end of the parent alkane and change to -ol. You add a position number before the suffix to include the location of the hydroxyl group. You give the priority to the hydroxyl group. So this would be propane 1-ol, propanol, propan 1-ol. If it was located at this carbon, it'd be 2-ol. This carbon, still 1-ol, still the beginning. So let's take a look at this one. Now, if you have more than one hydroxyl group, you leave the E in front of the parent alkane and you put diol or triol or tetraol. For example, here, ethane 1,2-diol. 3 carbon, propane 1,2,3-triol. You then number any side chains, any branches, give the product to the alcohol group, and you add these branches to the prefix. 2,3-dimethyl butane 2-ol. Let's go through this. We know that butane, methane, ethane, propane, butane. 4 carbons. 1, 2, 3, 4. 2-ol, the hydroxyl group is at carbon number 2. We're going from right to left, carbon 2. On carbon 2, we also have a methyl group. And on carbon 3, we also have a methyl group. And of course, we fill in the hybrids. 2,3-dimethyl butane 2-ol. So, cyclohexanol, hexanol, cyclo, 1, 2, 3, 4, 5, 6 carbons with an OH group attached. Phenol, 6 carbons, 6 carbon ring, benzene ring with a hydroxyl group attached to it. Now, we go C5H11 that are pentanols. Well, 1, 2, 3, 4, 5. 1 pentanol. It was attached to carbon 2, 2 pentanol, carbon 3, 3 pentanol, depending on where the OH group is attached. So in turn, alcohols, they have that hydroxyl group. Now, alcohols are formed through a process of elimination reactions. An alkene plus water, the aid of a catalyst, the double bond splits, an OH goes on. The OH on one side of the double bond, the H on the other. They can also be formed by elimination reaction going the other way, where the double bond is reformed. If you take an alcohol, such as in this case, ethanol, it can be broken where the H and OH come off to reform water, reforming ethene. Now, if you have an organic halide in a strong base, hydroxide, what happens is double bond reforms, the halogen comes off, yielding water and the halogen. We'll talk more with the reaction a little later. So the next group are the carboxylic acids and esters. Use carboxylic acids all the time. Vinegar is a carboxylic acid. So let's take a look, folks.
Carboxylic acids are found widely in nature. Here are 3 examples. First up, methanoic acid. Methanoic acid is commonly called formic acid, from the Latin for ant, formica, as it is the compound red ants inject into their prey. It was first isolated by distilling red ants. Secondly, ethanoic acid. Ethanoic acid is commonly called acetic acid, from the Latin acetum, meaning sour wine. This is because wine, which is a solution of ethanol, is oxidized in the air to ethanoic acid. Vinegar is a dilute solution of ethanoic, acetic acid. Then, ethane dioic acid. Ethane dioic acid commonly called oxalic acid, is toxic and is found in rhubarb leaves, and that is why we should never eat them. Carboxylic acids contain the carboxyl group, as shown in the video. This is made up of a carbonyl group and a hydroxyl group. Let's have a look at the reactions of carboxylic acids. Carboxylic acids react as typical acids. These are, number 1, acid plus metal goes to salt plus hydrogen. For example, ethanoic acid plus sodium to sodium ethanoate and hydrogen. Number 2, acid and base goes to salt plus water. For example, ethanoic acid and sodium hydroxide become sodium ethanoate and water. And 3, acid plus carbonate go to salt plus carbon dioxide plus water. For example, ethanoic acid and sodium carbonate to sodium ethanoate, carbon dioxide and water. Carboxylic acids also give another important reaction called esterification. Here they react with alcohols to give an ester plus water. An example is ethanoic acid and ethanol to ethyl ethanoate and water. This is a reversible reaction, which can be seen from the directions of the 2 arrows shown. In this reaction, a few drops of concentrated sulfuric acid are added. This sulfuric acid acts as both a catalyst and to remove the water formed, thereby displacing the equilibrium to the right following Le Chatelier's principle. If you don't know this principle yet, no problem. We have a video about it right here just for you. Now, let's take a look at what esters are actually used for. Esters have characteristic smells and are responsible for the flavour of foods and smell of flowers. They are therefore useful as flavourings and perfumes. Some examples of esters, together with their smells, are 3-methyl-butyl ethanoate, or bananas, pentyl ethanoate, pears, and octyl ethanoate, oranges. Animal fats, vegetable fats and oils are esters of long-chain fatty acids and glycerol. A soap is a salt of a fatty acid. Check out our water and soap video. So, to recap, carboxylic acids contain the carboxyl group. They show the typical reactions of acid. With alcohols, they undergo esterification to produce esters, and esters are used in the catering and cosmetic industries.
So with that being continued on, remember, with carboxylic acids, these contain what is known as a carboxyl group. Carboxyl is simply a carbon with a double bond oxygen with an OH group as well. When this group is attached to it, they're said to be a carboxylic acid, and they're named accordingly. In fact, what happens is the chain plus oic acid. Benzene plus a carboxyl group, benzoic acid. Methane, 1 carbon, methanoic acid. 2 carbon, ethanoic acid, and so forth. These carboxylic acids are weak organic acids, and they do have chemical properties that indicate as such. So in naming them, we start with the parent alkane. We replace the E with the name oic acid. And the carbonyms are always given preference number 1. So to draw methyl 3-methylbutanoic acid, we start butane, 1, 2, 3, 4. 4 carbons of butane. 4 carbon. We've added the carboxyl group, which is one of the carbons. It takes precedence. This is carbon 1. So 1, 2, 3. We add a methyl group here, and this would be 3-methylbutanoic acid. This one here, we see COOH. We know it's a carboxylic acid. 2 carbon. So 2 carbons with the carboxyl groups on one of them, making it ethanoic acid. We have 3 carbons attached as well. Can't attach here, it's already full, so it must be right here. Trichloroethanoic acid. As for 3-propyl octanoic acid, octane, 8 carbons. With a carboxyl group. On carbon number 3, we have a propyl group, methane, ethane, propane, 3 carbons. Carbon 1, carbon 2, carbon 3. So we attach a 3-carbon side chain. 3-propyl octanoic acid. As for esters, esters are formed when carboxylic acids react with alcohol. H from the alcohol combines with the OH group from the carboxylic acid to yield the ester plus water. This reaction, because water comes off, condensation, or it creates an ester, an esterification reaction. Now, the functional group is similar, but on the other end, the oxygen is not an H, it's the rest of the carbon. So they're very flavorful, creates flavorings, creates there, all kinds of things around esters. Here's the functional group here. You can see listed. So, examples. When you smell an apple, when you smell an apricot, it's banana, and so on. This is all created because of the ester that's there. So esters have 2 distinct parts, an alcohol part and a carboxylic acid part. The main part contains the carboxyl group, which comes from the parent acid. The second group, the alkyl group, comes from the alcohol. So to name them, you identify the main part, which contains the carboxyl group. This comes from the acid. You begin by naming the parent acid, but the oic acid gets changed to O8. Propanoic acid becomes propanoate. The second part is the alkyl group. It's considered a side chain. You name it as you would any other side chain. 1 carbon side chain, methyl. So the name would be methyl propanoate. When you combine propanoic acid and methanol, methyl propanoate. Of course, water comes off as a result. So naming esters, let's take a look. The name of this would be 1, 2, 3, 4 methane, ethane, propane, butanoic acid. Combining with a 2-carbon ethanol. When it combines, butanoic acid forms the main part. So this would make this butanoate. And the alcohol part, so it becomes ethyl butanoate. And of course, water comes off as well. Now let's name this one. We have benzoic acid. Combining with methane, ethane, ethanol. The main part, the acid, becomes benzoate. Ethyl group. So it's ethyl benzoate. Of course, one of the products is water comes off as well. So, looking at carboxylic acids and esters, carboxylic acid, the functional group is the carboxyl group. Ester, it's the alkylated carboxyl group. When you combine alcohols and an ester, you end up, alcohol and carboxylic acid, you form the ester and water as well. Now, so butanoic acid reacting with methanol forms methylbutanoate in water by way of an example. So let's take a look at this. The molecular form for 2,5-dimethyl-cyclohexanol. Oh, we got an OH group. So let's take a look at what this would look like. Cyclohexane, 1, 2, 3, 4, 5, 6 carbons. An OH group attached to it. And 2,5, so carbon number 2, we have a methyl group. At carbon number 5, 2, 3, 4, carbon 5, we have a methyl group. Of course, each of these carbons, each of them, exception this one, this would have a single H. So carbon with an H, CH2, CH2, again, all will have 4 total bonds. So how many carbons do we have? We have 6, 7, 8 carbons, 8 of them. 2 side chains, so we know that it can't be this one or this one. How many hydrogens do we have? Well, we have 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. 16 hydrogen attached to it. So the answer is D. This one here, next 2 questions. Butanoic acid, methanoic acid, octanoic. Butanoic acid can be described as an aliphatic, because it doesn't have that benzene ring, so it's not an aromatic. Because it's a butanoic acid, it contains a carboxyl group. Functional group is carboxyl. It's a carboxylic acid after all. How about this one? To form out their isomers of C5H10 are numbered. Which ones are isomers of C5H10? Carbon 5, cyclopentane would be. Pentene would be. Again, notice it's C to the N, H to the 2N. It wouldn't be any of the alkanes except for the one that is a ring compound. Here and here. So 1, 3, ethyl cyclopropane, methyl cyclobutane, methane, ethane, propane, 4, 5 carbons, 4, 5 carbons. So 6 and 7 will be there as well. 1, 3, 6, and 7. Structure description that apply to methyl cyclopentane. Methyl cyclopentane. So cyclopentane would be 2. All single bonds. So it's an alkane. It's saturated. Can't put any more on there. Then the question is it branched or unbranched? Well, it does have a branch, this methyl group. So 2, 4, 6, 7. 2, 4, 6, and 7. Mixture of liquid methanol and liquid ethanol can be separated by, we can distill it, boil it down, the cracking process. And these compounds that allow them is their boiling points. So this brings to the last section here, which is looking at organic compounds and how oil is a very important organic chemistry component here in Alberta for sure. So let's take a look at what fractional distillation actually involves.
In this video, you will learn how fractional distillation separates crude oil into useful fractions. Crude oil is the term used to describe unprocessed oil. That is oil that has been taken directly out of the ground, either on land or under the sea. It is an exceptionally valuable resource. It provides us with a great number of hydrocarbons, some of which are useful as fuels, and others are used in the manufacture of many different chemicals and even plastics. However, in the raw form as crude oil, it can be a viscous, dark-coloured tar-like consistency, and the different fractions of hydrocarbons must be separated by fractional distillation for them to be useful. Before we understand how fractional distillation works, we should be clear that crude oil is a mixture of hydrocarbons with different chain lengths, some being short molecules and some being very long. Intermolecular forces act between molecules, and the longer the molecule, the greater the intermolecular force. As you can see here, the small molecules have weaker intermolecular forces, and so will require less energy to break them apart and turn them into a gas. They have a lower boiling point. The longer molecules have greater intermolecular forces. More energy is required. A higher temperature will be needed to evaporate these molecules. They have a higher boiling point. Now we understand how chain length is related to the boiling point of a molecule. Let us look at how this method works. As you can see, crude oil is heated up to a high temperature outside of the fractionating column. The hot crude oil, now mostly in vapour form, is pumped into the column. The column has a heat gradient and is very hot at the bottom, going cooler as we move up to the top. Even at the very bottom of the column, where the temperature is still high, some long chain molecules with high boiling points begin to condense back into a liquid. These are collected at the bottom of the column. The rest of the molecules start to rise up the column, making their way through bubble caps in each tray. The bubble caps slow down the rate of the rising vapour, and eventually the vapours get too cool, condense, and are collected as liquids in the trays. Small molecules have low boiling points, and so condense much higher in the column, where the temperature is cooler still. As you can see, hydrocarbons with similar boiling points are collected in the same tray, and this is why they are known as fractions. They are mixtures of hydrocarbons with similar boiling points. Each fraction has some important uses. Some examples of fractions are petrol, useful as a fuel for cars; naphtha, used in the manufacture of chemicals; kerosene as aircraft fuel; diesel oil, used as fuels for vans, cars and lorries; and bitumen, a mixture of large chain hydrocarbons used to lay roads. Now, at the end of this video, you should understand that crude oil is a mixture of important hydrocarbons, and that fractional distillation is the method used to separate crude oil into useful fractions with similar boiling point. You should understand that small chain molecules are collected at the top of the column since they have lower boiling points, and larger chain molecules are collected further down the column as these have higher boiling points.
So, Hassan, that's an explanation of fractional distillation in terms of overall. Now, we know that various properties of alkanes, alkenes, alkynes, and branching molecules contribute to what boiling points would actually be because of the differential intermolecular force that are actually played through, as we see here. So because of this differential nature, they can be separated into various components, be it the alcohols, be it the carboxylic acids, be it the esters, based on how they actually differentiate. as per their boiling points. Now, if you look at butane, it's used as fuel. A single butane has a molecule total of how many carbon? Well, it's going to have 4 carbon-to-carbon bonds. Because it's an alkane, it's going to be saturated or aliphatic hydrocarbon. Now, from the program of studies, you're expected to understand the process of fractional distillation, which is outlined in the video. So when crude oil is refined, we take advantage of these boiling points to separate them in accordance with that. So these fractional distillation towers contain trays located at various levels. Heated crude oil is inserted at the bottom. As it rises, it starts to cool. As it cools, the different components condense out at different levels based on what their corresponding boiling and melting points are. The bottom's kept hot and the temperature gradually decreases. As it rises, it condenses, and these fractions get withdrawn at various heights along the tower. Now, in more detail, again, it rises, it cools. To get from one to the next, it bubbles through different condensation trays. And you can see the bubble caps that are used to allow this to happen. Now, if it cools to its boiling point, it condenses and is piped off. Now, the greater the number of carbons, the greater the boiling points, which means the longer it actually has to come off there. So you get the higher boiling points and the lower boiling points accordingly, based on that principle. So the other thing that's done is large hydrocarbons get broken into small ones through a process of cracking. Typically, historically, it was thermal cracking. High temperatures create a large quantity of something called solid coke. Now, catalytic crack is more, these use catalysts to speed up the reaction, produce less products such as tar, asphalt, so on. So notice you're going from larger to smaller in carbon. In the 1960s, hydrogen was used and incorporated. Hydrogenation helps us do larger molecules, add hydrogen, you get smaller molecules. Of course, the molecules split, you have to add hydrogen in, take up the space in between. So let's take a look at exactly what cracking is.
In this video, you will learn about the process of cracking, how it is carried out, and why it is done. From our video on fractional distillation, you should know that crude oil is a mixture of hydrocarbons with different carbon chain lengths. Smaller hydrocarbons have a lower boiling point and are more volatile, making them easy to ignite and more useful as fuels. Larger hydrocarbons have a higher boiling point, are harder to ignite, therefore not as useful as fuels. We use a lot of fuels in our day-to-day lives, driving cars, aeroplanes, lorries, and even heating our homes. This means there is a very high demand for small chain hydrocarbons. However, after fractional distillation, we find that we have a large supply of long chain molecules. The process of cracking breaks down long chain alkanes into a smaller alkane and alkene molecule. This allows the supply of short chain hydrocarbons to meet the demand for them, as the longer chain alkanes are broken down into shorter alkanes and an alkene. The alkenes are also useful as these can be used in the manufacture of plastics. Here is an equation showing that C12H26 is broken down into octane and butene. There isn't a set way that these molecules are broken down. In fact, C12H26 could also be broken down into decane and ethene, or even butene, pentane and propene, as these equations show. The large hydrocarbon is broken down in quite a random way. Just note that in each equation, of course, since we had 12 carbon atoms and 26 hydrogens going into the reaction, the same must come out. The process of cracking is carried out in one of two ways, either by thermal cracking using high temperature and pressure, or by catalytic cracking at low temperatures and pressures but using a catalyst. In thermal cracking, the large hydrocarbons are heated to temperatures up to 750 degrees C and a high pressure of 70 atmospheres. This high temperature and pressure breaks the bonds between carbon atoms to make smaller molecules. Catalytic cracking is the method used mostly in industry today. The large hydrocarbons are heated to around 500 degrees C and are passed over a zeolite catalyst. The catalysts chosen tend to break the bonds in the large hydrocarbons and make molecules of between 5 to 10 carbons in chain lengths, making them very useful in petrol. Now, at the end of this video tutorial, you should know that cracking is the process in which large alkanes are turned into smaller alkanes and an alkene molecule, and that there are two types of cracking: thermal cracking using high temperature and pressure, and catalytic cracking, which is the method preferred in industry as it uses lower temperature and pressure and produces more molecules that are useful in petrol.
So that video outlined the process by which crackers. We've looked at, of course, how oil is refined through physical processes such as fraction distillation and even solvent extraction, dissolve and taken off, but also chemical processes such as cracking and reforming. Now, these chemical processes are needed because fraction distillation doesn't produce enough of what's in demand, but it also produces too much of the heavier fractions. So you need to have some method to get to what the more valuable product actually is. So these cracking units with a catalytic converter actually allows for this cracking process to break chains into smaller chains, and these smaller chains are often the more valuable ones. So from a prime methanol, produces formaldehyde, and you can see on this page here, again, a copy from your textbook, all the different fractions that can be derived from crude oil petrochemicals. Very useful for us. We see that the catalytic reforming process in alkylation also helps improve what's happening, what products we're getting. Again, this is covered off on page 392. And alkylation improves the quality of the fuel, giving more branching. Again, isomerization converts molecules into a branched isomer, which has more power and more pep behind it. I'd suggest you read your textbook for that as well. So, in essence, an oil refinery is a combination of the distillation column, the boilers, the crude oil going in, and there's a fractional distillation process. It also involves a reformer. It involves a cracking unit and alkylation units to get the more valuable products. In essence, from petrochemicals, we know it's very significant. Yeah, there's risks and benefits, and we can get all kinds of ethane, for example, cracked into ethene, and then convert to other products. Plastics, paints, and the list goes on. And let's not fool ourselves. There's a lot of very well-paying careers in petrochemical and be a worthwhile career choice. Thank you for your attention. We'll see you next day.